Okay, so I need to talk a little bit about what the ideal gas law is. One of the things you've learned previously is that when we think of volume of a gas and its pressure, if you change the volume of the gas, the pressure will change as well, but they're inversely related. So if you increase the volume of a gas, the pressure will go down. Here, you're holding the moles and the temperature of the gas constant. We've also learned about Charles' law in that the volume and the temperature of gas are directly proportional. You increase one, you increase the other. In this case, you would have to keep the moles and the pressure of the gas constant. Avogadro's law is the relationship between the volume and the moles of the gas, and so they are directly related. Again, increase one, increase the other. Avogadro's law applies when you hold pressure and temperature constant. Now, if you wanted to, you can sort of combine these proportionalities into one equation. And so I've done that there. And you can see that volume is going to be directly proportional to moles, which is N, and temperature, but inversely proportional to pressure. And so one of the things that you already know is you can take that proportionality between volume and NT over P and turn that into an equality if you add some kind of numerical constant. So I've done that there. Here I say V is equal to constant times NT over P, and now we're not going to call the constant K anymore. We give it a special letter. We're giving it a capital R. So V is equal to R, which is the constant, times N times T divided by P, and then you can sort of rearrange variables, and then we sort of get the common expression of this new gas law we're going to deal with, which is PV is equal to nRT. This law is called the ideal gas law. So the thing to sort of note about the ideal gas law is it's a little bit different than the gas laws you sort of used in the past. With the gas laws you used in the past, usually in the problem what you would have is you would have some initial conditions, and then what you wanted to do was define a property of the gas maybe at some new conditions. But here it's a little bit different. Here we're just looking at a gas at the same conditions. And here within those conditions you may be given, say, three properties. For example, you might be given, say, a volume or moles and temperature of the gas. And from those properties at those conditions, you just find the pressure. Now, one of the things you need to worry about is the value of R. And so that will be given to you on a test. But just to note that this constant, this R, which is in that equation, can have different values depending on what the units are going to be in that equation. So for example, if you're given a volume in liters and you're given a pressure in atmospheres and you have moles and a temperature in Kelvin, R would be equal to 0.08206. However, in a problem, if you were given a volume not in liters but in milliliters, but you had atmospheres in Kelvin, then R would be a different value. It would be 82.06. You might, instead of having pressure in atmospheres, you might have it in a different unit like kilopascals, and then R changes its value again. And so there are all these different values of R depending on what the units are for the properties of the gas. And so the best way to sort of deal with that in a problem is probably just use this first value of R, which will be given to you on a test, which is 0.08206 liters atmospheres over moles degrees Kelvin are the units for the constant. And so if you are given a problem, you can use that value of R if you take each of those properties of the gas and make sure they are in the appropriate units that you see there. So volume must be in liters, pressure must be in atmospheres, and temperature must be in Kelvin. And then there's going to be some kind of amount of gas which will hopefully be in moles. So let's go ahead and do a practice problem given that information. We have sulfur hexafluoride is an odorless, colorless, very unreactive gas. Calculate the pressure in millimeters of mercury exerted by 1.82 moles of the gas in a steel vessel at 5.4 liters at 72.5 degrees Celsius. Okay, so let's go ahead and assign some variables here. We're going to try to find the pressure of the gas. So I'm going to put a question mark here. We have the number of moles of the gas, which is 1.82 moles. And so it's contained in a vessel, and so the volume of that vessel is 5.40 liters. And then the temperature of the gas is 72.5 degrees Celsius. So I think what you can sort of see with this problem is we have initial conditions here, but we don't have new conditions that we're converting this gas to. We're looking at the initial conditions, and given we know the moles of the gas, the volume of the gas, and the temperature of the gas, can we find the pressure of the gas? And the answer is yes, we can, using the ideal gas law. And so the pressure here is P times V is equal to nRT. And so we can solve for P using this law. And so R, let's just write this out, it's 0.08206, and the units are liters, atmospheres, over moles, degrees Kelvin. So what we have to do to use this formula is we have to make sure that we have all these properties in the correct units. So volume is in liters, which is good. We have an amount of gas in moles. We will have to convert this temperature into Kelvin. So it's going to be plus 273.15. And again, I'm going to use that trick that the book does where we work out what the temperature is in Kelvin by adding 273.15 and then rounding it at this point to the correct number of significant figures, plus 273.15. And so I get on my calculator 345.65, but note the uncertain digit in 72.5 is here, the uncertain digit in 273.15 is here, and so here I think this is going to be 345.7 rounded to the correct number of significant figures, and this is in degrees Kelvin. Okay, so at this point what we can do is we can plug this into the ideal gas law. But first, let me go ahead and solve this for P. So you can work it out on your own, but P should be equal to nRT over V. Okay, so let me go ahead and just plug in numbers here and see what we get. N is going to be 1.82 mole. R is 0.08206 liters, atmospheres, over moles, degrees Kelvin. And then, let's see, the next thing we need to have is T, which is 345.7 degrees Kelvin. And then what we have finally is volume, which is 5.40 liters. And so let me just confirm that the units cancel as expected. So moles here cancels, liters cancels here. We have an Kelvin cancels, and so we're left with atmospheres in R. And so when we plug in these numbers, we'll get a pressure in atmospheres, which we'll have to convert into millimeters of mercury. So let's go ahead and work that out. So it's going to be 1.82 times 0.08206 times 345.7 divided by 5.4, and I get for a pressure 9.56. I'm going to round this to correct number of significant figures at this point because that's what the book does after you plug in numbers into the equation. So it should be 3 significant figures. So I get 9.56 atmospheres. Now that's not the answer. We really had to convert this into millimeters of mercury. So I'm going to multiply it by 760 millimeters of mercury. I think these 3 digits are considered significant over 1.0 atmosphere. 1 is an exact number. And so what do I get? I get times 760. And so I get, rounded to the correct number of significant figures, I get 7270, should be 3 significant figures, millimeters of mercury. And if you wanted to, you can convert this into scientific notation. So that should be the answer there. Okay, so let's move on. One of the things you can do is you can take the ideal gas law and derive all the other gas laws from it. And so let me just give you sort of an example of that for taking the ideal gas law and deriving the combined gas law from it. This is how you would go about doing it. So you write out the ideal gas law twice. So here I'm doing it for condition 1, the initial conditions, which is P1 times V1 equals N1 times R times T1. And then you write next a bar, and then you put in the final conditions underneath the bar in the denominator. So it's P2V2 is equal to N2RT2. So let's say we write that out, and we want to write out an expression that relates the pressure, volume, and temperature of gas in initial conditions compared to the final conditions, but moles, and we're going to keep that constant. Here, what I'm just sort of doing is separating this equation into two portions, and so there's an equal sign in the middle. What I want to do now is just go ahead and we can cancel out the r from this equation because the r value remains constant whether the r is in the first equation or the second equation. It's the same number. And then here we're holding moles constant if we're looking at the relationship between pressure, volume, and temperature of a gas between these two conditions. And so if the moles are constant, that means the moles in the initial condition, N1, is going to be equal to the moles in the final condition, N2. And so that can be canceled out. And so after you cancel out the property that remains constant and that constant R, this is what you're left with, is P1 times V1 over P2 times V2 is equal to T1 over T2. What you can do is move variables around, and then that is there on the right, the combined gas law. Again, what you can sort of see is that if you write out the ideal gas law twice under two different conditions, put the first condition in the numerator, the second condition in the denominator, if you cancel out the variables that remain constant between these two conditions, you can derive the relationship between the other variables in these two different conditions. So let's go ahead and solve a problem where we're doing that so you can sort of see how this is applied. So you have 2 moles of a gas at 2 liter volume in a flexible container, and it's at 1 atmosphere pressure. Let's say you add 1 mole of gas to this flexible container, and the pressure increases to 1.2 atmospheres and expands to a new volume. Assuming the temperature does not change, what is the new volume of the container? Okay, so this help me get my bearings here. What I want to do is assign variables, and that can help me focus as to whether I know a gas law that can be used to solve the problem. Okay, so we have initial conditions where we have moles, we'll call it N1 is 2.00 moles. And then we have volume of a gas, so it's V1 is 2.00 liters. And we have a starting pressure as well. P1 is equal to 1.00 atmospheres. Okay, so far so good. Let's say you add an additional 1 mole of gas to this flexible container, and the pressure increases to a new pressure, 1.2 atmospheres, and expands to a new volume. What is the new volume of this container? Okay, so we now know some new conditions. So the new number of moles at the new conditions, N2, will be, it looks like we're going to take the original number of moles and add just another 1 mole to it. So the new number of moles is 3.00 moles. We're trying to find the new volume V2, right? We are given the new pressure, which is 1.2 atmospheres. Okay, so we're basically trying to find V2. Now, I think you can sort of see, at least right now, I can't think of a gas law that I can immediately apply to this that I know of that could solve for V2. And the reason is, when I think about Boyle's law is relationship between pressure and volume of a gas in two different conditions, given that temperature in moles is constant. We cannot apply that here, because in this problem, you can see we have pressure and volume changing, but we also have the number of moles changing. So what we have to do is we have to derive a new expression that relates the pressure, volume, and number of moles of a gas at these two different conditions. And we're going to have to derive it from the ideal gas law. So let's go ahead and try doing that. So the ideal gas law is P1V1 is equal to NRT1. Let me put a 1 here by the moles here. And so we're going to divide that by P2V2 is equal to N2RT2. So what we're going to have to do is we're going to have to derive an expression between volume, pressure, and moles of a gas of these two different conditions. And so to go ahead and do that, let's cancel out the variables that remain constant. So one variable that remains constant is R. Another variable that remains constant in this problem, according to the problem, is temperature. That does not change. So we can sort of write this now like this. Let me get a new pen. So it's going to be P1 V1 is equal to N1 over P2 V2 is equal to N2. So what I can do further is break this up into two portions like this. P1 V1 over P2 V2 is equal to N1 over N2. Now, what we want to do is we want to compare initial conditions to final conditions. So let's get the initial conditions on one side of the equal sign and the final conditions on the other side. So I'm going to move N1 here to the denominator on the other side of the equal sign. I'm going to move P2 V2 here in the denominator to the other side of the equal sign. So let's see what we get. So we get P1 V1 is equal to N1, or divided by N1 is equal to P2 V2 divided by N2. Okay, so it looks like we can use the expression to solve the problem. So what you would have to further do is you would have to solve this for V2. So I'm going to have to move the N2 over to the other side of the equal sign, goes in the numerator, and the P2 I'm going to have to put on the other side of the equal sign in the denominator. So what I get, I'm going to write this over here, is V2 is equal to P1 V1 times N2 over P2 times N1. So let me just kind of plug in numbers really quick and let's see if we get the right answer really fast. So it's 1.00 atmospheres is P1. Volume 1 is 2.0 liters. And so N2 is 3.0 moles. And it looks fine so far. P2 is going to be 1.2 atmospheres. And N1 is 2.0 moles. Let's see if we get the correct answer here. Hopefully we do. So it's going to be 1 times 2 times 3 divided by 1.2 divided by 2. So I get 2.5, and I think all the units cancel out in such a way that should give you liters. And so that should be the answer. Okay, so let's move on to a new problem. The final thing we need to go over is the relationship between the molar mass of gas and its density. And we can sort of figure out the relationship between those two variables using the ideal gas law. So here I sort of take the ideal gas law and derive a new equation that relates the molar mass of gas to its density. But I think the thing for me to do is to go ahead and write that equation here on the screen. All right, so the equation is as follows. And so you might remember the ideal gas law as PV is equal to nRT. So you could derive this new equation if you want to. I'm just going to give it to you. So it's P with the weird looking M that looks like this is equal to dRT. So P is pressure for a gas. Weird looking M is the molar mass of gas. And so you know the units for molar mass are grams per mole. And then D here is density of a gas. And so the units here are a little something that we haven't seen before for density. They're not grams per milliliter, which is what we're used to seeing for density, or grams per cm cubed. They are grams per liter. Okay, so the way I remember this equation, I think of nighttime dirt. So nighttime PM, DRT, dirt. Nighttime dirt, and that helps me remember what the equation is. Okay, so let's go ahead and use this equation to solve some problems. So I've got a problem here. It says calculate the average molar mass of dry air. In other words, air with no water vapor in it, if it has a density of 0.0117 grams per mil at 21 degrees Celsius and 740 millimeters of mercury pressure. Essentially what we're going to try to do is we're going to try to find the molar mass of the gas given its density, and we know its pressure and its temperature. So let's first assign variables and see where we're at first. So the density is, we have a value for that, which is 0.00117 grams per mil. Okay, so remember when we use this equation that relates density of a gas to its molar mass, we have to take any density and get that into grams per liter. So we would have to convert this. So it'd be 1,000 milliliters per 1 liter. And I think if you work that out for the density, it's going to be 1.17 grams per liter. Okay, so that's good. So we have a pressure of 740 millimeters of mercury. Okay, so when we use the equation PM dirt, we have to get the pressure into atmospheres. And the reason is because our value of R is still the same. Our value of R is liters, atmospheres, moles, degrees Kelvin, so the pressure here must be in atmospheres. So it's going to be 740 millimeters of mercury times 1 atmosphere over 760 millimeters of mercury. And so the millimeters of mercury cancels out, so it's going to be 740. Let me work this out really quick. Divided by 760. 740 divided by 760 is going to be 0.97. I'm just going to round it off now, as the book suggests, 0.974 atmospheres. And then the next step is we have to get temperature probably into Kelvin, unless it's given to us in Kelvin. Is it? No, it's not, unfortunately. So it's 21 degrees Celsius plus 273.15. And so I get 21 plus 273.15. I'm going to round this. Two significant figures at this point. So it's 294 degrees Kelvin. Is there any other information we need? R, of course, is 0.08206 liters, atmospheres, over moles, degrees Kelvin. Okay, so what we would have to do to solve the problem at this point is do a little bit of algebraic manipulation and solve this equation for M. So I'm going to do this really quickly. So M is equal to dRT over P. And then at this point, it looks like you just plug in numbers. So let me just go ahead and throw in the numbers. So we have, again, density must be in grams per liter. So it's 1.17 grams per liter. R is 0.08206 liters, atmospheres, over moles, degrees Kelvin. And then finally, we have a temperature. It looks like I'm going off the screen here, so I'll just write it up here. The temperature is going to be 294 degrees Kelvin divided by the pressure, which is going to be 0.974 atmospheres. And so our answer should be 29 grams per mole. So let me just confirm that the units are going to be in grams per mole. So we can see that atmospheres cancels, Kelvins cancels. It looks like we have grams per liter and liters per mole. So it looks like liters cancels. And so we will have an answer, it looks like, in grams per mole. So I think when you do the math, and it turns out to be 3 significant figures, it should be 29.0 grams per mole. Okay, so let's move on to a new problem. Okay, so we're going to do one more problem using this equation. And so this is a kind of a neat problem, because what you can see is we don't have a lot of numerical information here, and yet we can use this equation and the conditions of standard temperature and pressure and still give us an answer. So what is the density of nitrogen gas at standard temperature and pressure? So again, we're going to use this equation, which is PM dirt. So the pressure times the molar mass of the gas is equal to density of gas times the gas constant times the temperature. So let's go ahead and solve this now for D and see where we're at. So density of the gas is equal to pressure of the gas times the molar mass over R times T. So let's see if we can sort of find numbers for these variables and see if we can get an answer to that. Okay, so I think it won't be too difficult to do. So if we're at standard temperature and pressure, we know what P will be. So I'm just going to write that in. So it's going to be 1.00 atmospheres. The molar mass, even though that isn't given to us in this problem, what we can do is we know the identity of the molecule. And since we know the identity, we can figure out what the molar mass for that molecule is going to be. So it's diatomic nitrogen. Each nitrogen atom has an atomic mass of 14.0 grams per mole. You can look that up in the periodic table. So if we have 2 atoms, and so the molar mass for N2 should be 2 times 14, which is 28.0 grams per mole. So I'm just going to write that here, 28.0 grams per mole. And then over R, which is 0.08206 liters atmospheres over moles degrees Kelvin. And then T, what you would have to do is at standard temperature, which is what we're at, that's 0 degrees Celsius, we have to get that into Kelvin, so that's 273.15 degrees that you add to 0. And so that's going to be rounded to correct number of significant figures, 273 degrees Kelvin. So I think if you go ahead and plug in those numbers, what you would do is you get 1.25. And so if we wanted to, it's not a bad idea to see if the units cancel in such a way that leaves us an answer in the units that we want, which is grams per liter. So atmospheres cancels here, moles cancels here, temperature cancels here. So it looks like we're good so far. So we have grams left in the numerator, liters in the denominator, so it's in grams per liter. Now, let me show you a second way that you can solve the problem, which is kind of interesting. If you can remember this relationship, it only applies at standard temperature and pressure, but it could be useful in quickly solving a problem where you have to find the density of the gas. That relationship is as follows. The density of the gas at standard temperature and pressure is equal to the molar mass of the gas over the molar volume at standard temperature and pressure. And so let's go ahead and quickly see if we get the same answer but using this equation. 28.0 grams per mole over 22.414, and it's going to be liters per mole. See, dimensional analysis saves me. Okay, so what you can see is that the moles cancel, and so we should get an answer in 1.25 grams per liter, which should be the answer. Okay, thank you for listening, and we will see you next time.